Let me welcome you to this lecture. We have been discussing the chemistry of pi complexes, that is, we have discussed the chemistry of metal olefin complexes and bonding as well as reactivity in metal olefin complexes. So let us now discuss the chemistry of metal alkyne complexes or complexes formed by the alkyne ligand. These complexes are interesting because of several reasons, and uh, many of these complexes actually are thought to be important intermediates in the cyclooligomerization of alkynes, as well as the reactions of acetylene with metal carbonyls gives a very interesting array of products, and that is why the chemistry of metal alkynes have drawn a lot of attention in recent times. So now if you look at the compounds, metal alkyne complexes, there are several binding modes of the alkyne ligand are observed, and the most common binding modes of the alkyne ligand is this is a monodentate binding mode of the alkyne ligand. Then we can also have bidentate binding mode. That is formation of a chelate in this way. And these two binding modes, the alkyne ligand essentially acts as a 2-electron donor. Now the alkyne ligand can bind to metal centers like two orthogonal alkene units, because the two the two pi bonds in alkyne are, we know, are in orthogonal planes, and that is why both of these two pi bonding molecular orbitals which are orthogonal to each other can bind to metal centers in an orthogonal, as if two orthogonal alkenes are binding to the metal center. So depending on that, actually there are different other types of binding modes of the alkyne are possible. So here the alkyne bridges two metal centers, and two different pi bonding molecular orbitals are used to bridge the metal centers in an orthogonal way. And this is again a bidentate binding mode, and it's a 4-electron. The alkyne essentially acts as a 4-electron donor in this case. Now we can also bind or bridge metal centers with this sort of a binding mode, where the two metal centers are essentially bridged in this fashion. This is a tridentate binding mode. Then we can also have tetradentate binding mode, where the alkynes bridge two metal centers in this fashion, where the alkyne ligand now acts as a tetradentate ligand. So now in these cases, in these three binding modes, the alkyne ligand acts as a 4-electron donor, which is 4-electron donor. So this binding mode, that is the 2-electron donor binding mode, these two binding modes are essentially observed in case of electron-rich metals. The alkyne acts as a 2-electron donor, and when complex to electron-4 metals or alternation metals, the alkyne ligand essentially shows a 4-electron donor behavior and uses one of these binding modes essentially. So these are the binding modes of the alkyne ligand, and now we'll see the preparation of metal alkyne complexes, where the alkyne ligand essentially acts as a monodentate or a bidentate ligand, and thereafter we will discuss preparation of metal alkyne complexes where alkyne acts as a bridging ligand. So first we will discuss the preparation of metal alkyne complexes where the alkyne acts as a monodentate or bidentate ligand. So let us these preparative methods essentially uses ligand substitution or substitution of other ligands by an alkyne for preparation of metal alkyne complexes. So you can take this platinum complex and react it with ditersybutyl acetylene. In the first step, it is treated with ditersybutyl acetylene for substitution of the chloride, and in the second step, it is treated with an alkyl amine to give us the final product where the alkyne is bonded to the metal center in this way, and two of the chlorides are replaced. One of the chloride replaced the coordination side on one of the that you get by removing one of the chloride is occupied by the alkyne, while the other side is occupied by the amine. In this way. So this sort of a product can be obtained by substitution of chloride by using the alkyne ligand, and the CC bond distance in this case, the alkyne CC bond distance in this compound is equal to 124 picometer, while the C bond angle, this particular bond angle, as we know in case of the free alkyne, the this bond angle is equal to 180 degree because alkynes are linear. The carbon is sp hybridized, but once it is coordinated to the metal center, the hybridization is no more a purely sp hybridization, and it deviates. It acquires some more p character. The carbon atom, the hybridization on the carbon atom has more p character, and the bond angle also deviates from linearity, and it is now, in this case, it is equal to 165 degrees. And also, if you we can look at the CC stretching vibration in case of for the alkyne group over here. We know that the C111C stretching vibration appears somewhere around 2200 centimeter inverse in case of the free alkyne. But once the alkyne is coordinated to the metal center, this CC stretching vibration decreases, and for this particular compound, new CC appears at 2028 centimeter inverse, which is substantially smaller than what you see in case of the free alkyne. So then we can let us look at preparation of another metal alkyne complex, that is, if you take Cp2 titanium CO2 and then react it with diphenyl acetylene. So one of the CO group is replaced or substituted by the alkyne ligand here, and this sort of a metal alkyne complex is formed after substitution of the one of the CO ligand from the titanium ligand, and this sort of metacyclopropene-like structure is formed, and the CC bond distance now in this particular case is equal to 128 picometer, which is higher than the CC bond distance that you see in case of the earlier platinum alkyne complex over here. In this case, the CC bond distance is 128 picometer, and this particular angle, that is C angle over here, is equal to 146 degree, which is much more smaller than, or the more deviation from linearity happens in this case, because the bond angle has now is farther away from 180 degree. So then let us look at another method of preparation of a metal alkyne complex, in which case a metal olefin complex is taken as precursor now, and when it is treated with diphenyl acetylene, this sort of a platinum alkyne complex is again formed, and in this particular case, the CC bond distance here is equal to 132 picometer, and the angle, alkyne angle C angle again over here is equal to 140 degree. So one particular important aspect that we have not mentioned about this particular titanium alkyne complex is that the CC stretching vibration in this compound appears at 1780 centimeter inverse, while the CC stretching vibration in this case, in case of this platinum complex, appears at 1750 centimeter inverse. So what we see from here, or what we have observed here, is that again, like in case of metal alkene complexes, where we could write two canonical forms. In one case, a metallocyclopropane-like canonical structure, while in another case, we could write a donor-acceptor canonical structure where the alkene carbon atom retains the sp2 hybridizations. In case of metal alkynes also, we can write two canonical forms. In one of the canonical form, the alkyne carbon atoms retains sp hybridization to a large extent, while in the other case, the alkyne carbon atom acquires more p character. The hybridization has more p character, and it deviates. The hybridization can no longer be considered as sp hybridization. So we can write metallocyclopropene-like canonical form, as well as we can write this sort of canonical form where the alkyne carbon atoms retains the sp hybridization to a large extent. So that is visible and a particular metal alkyne complex can be, which particular canonical structure is more important for a given metal alkyne complex can be understood by looking at these structural parameter as well as the spectroscopic parameter. As we see in case of this metal alkyne complex, the deviation of the CCC angle is not very high from the linear case, completely 180 degree from 180 degree, and also the CC bond distance in this case is more close to CC bond distance in case of free alkynes, which is equal to 120 picometer. And that is why we can say that this particular metal alkyne complex, the sp hybridization has been retained to a large extent, or the extent of the contribution of p orbital has not increased substantially, and also the CC triple bond order has not decreased substantially, so and so that the CC stretching vibration has not decreased as compared to the decrease that we see in case of the other two metal alkyne complexes. And for this particular metal alkyne complex, we can say that this canonical form is more important. Now, for this, the last metal alkyne complex here, we see that there is a large deviation from of this CCC angle from linearity, as the angle is now has now decreased to 140 degree, and also the CC bond distance now is more closer to CC bond distance in case of olefins, which is equal to 134 picometer. In case of free olefin, the CC bond distance is 134 picometer, while the CC bond distance that we see in case of this platinum alkyne complex is equal to 132 picometer and is very close to the CC distance that we see in case of alkenes. So again, this decrease in the CC stretching vibration is also considerably large in case of this platinum complex here as compared to what we see in case of this platinum complex over here, as the CC stretching CC bond order has now decreased from 3 in case of the free acetylene ligand, and since this or decrease in the CC bond order is substantially high in this particular case, where the carbon atoms have acquired higher p character, or the hybridization in these carbon atoms have higher p character, and that is why the bond order is now more close to 2 as compared to what you see in case of this particular platinum metal alkyne complex. So for this metal alkyne complex, the metallocyclopropene canonical structure is more important or more relevant, we can say. Now, as we have discussed in case of metal olefin complexes or metal alkene complexes, those metal olefin complexes which have electron withdrawing substituents on the olefin are more stable as compared to metal olefin complexes with electron donating substituents on the olefin. So that is true in case of metal alkyne complexes as well. Complexes where the olefin or metal alkynes which have electron withdrawing substituents form stable metal alkyne complexes, and this allows one to make metal alkyne complexes for those alkynes even which are otherwise unstable. So, for example, this dichloroacetylene is a very highly explosive substance, and but upon complexation with metals, it forms stable metal alkyne complex. So you can take tungsten hexachloride, and when you react this with Cl2C2, that is dichloroacetylene etherate, and this reaction is done in presence of tetrachloroethylene, and then it produces a dimeric compound, this sort of a dimeric compound, which upon treatment with tetraphenyl phosphonium chloride gives us an anionic metal alkyne complex, and tetraphenyl phosphonium, of course, acts as a countercation in this case. And this is, we see that this dichloroacetylene, which is otherwise highly explosive when in free state, forms stable metal alkyne complex, and that is possible because of the electron withdrawing nature of the substituents on the alkyne over here, which allows formation of stable metal alkyne complexes. So other alkynes which are thermodynamically unstable can also form stable metal alkyne complexes. Cyclohexyne is a highly unstable metal alkyne because of the ring strain, because the carbon atoms, when in sp hybridized state, has to be in linear geometry, but the ring structure in cyclohexyne does not allow formation of linear bonds in this case, and that is why, because of this ring strain, cyclohexyne itself is in free state is highly unstable in nature, but we can prepare stable cyclohexyne complexes that is with, when it is reacted with this triphenyl phosphine platinum complex in presence of sodium amalgam, these bromines are replaced pH3 . So this sort of complex is formed where cyclohexyne is coordinated to platinum, and it forms a stable complex because, or the stability is now has increased because whenever these metal alkyne complexes are formed, the carbon atoms acquire more p character, and this allows formation of band bonds as compared to, which is, which essentially produces ring strain when the cyclohexyne ligand is in free state, uncoordinated state. So because of formation of the complex, the ring strain is essentially released here. So similarly, benzene complexes can also be prepared. So that is, you can take tantalum and niobium complexes, aryl complexes here. And when treated, when heated, CH4 is lost. One of the CH3 group abstracts one of these aryl hydrogen atom, and they are lost as CH4 here, and this leads to formation of a this sort of benzene complexes are formed because now this benzene ligand, which is otherwise highly unstable, forms a stable metal complex because of this because of this again increase in the p character on the carbon atoms, the stable metal complexes can be formed. So the metal here is tantalum and niobium. These two metals, for these two metals, these complexes have been isolated. So benzene complexes have also been isolated, that is, which are again highly unstable. Benzene itself is highly unstable, but when complexed with nickel 0, it allows formation of stable benzene complexes. That is C6H2 is the formula of the ligand here. So this sort of nickel 0 complexes formed by this benzene ligand allows formation of stable metal alkyne complexes. So what we have seen is that complexation of alkynes or unstable, thermodynamically unstable alkynes leads to formation of stable metal alkyne complexes. And in fact, when the alkyne is coordinated to metal center, its reactivity decreases to some extent, and we will see examples of reaction where this has been exploited. Now we will discuss about preparation of metal alkyne complexes where the alkyne ligand acts as a bridging ligand. So one very important example of this type of reaction is reaction of dicobalt octacarbonyl dicobalt complex with alkyne ligand over here, that is this leads to formation of a dinuclear metal alkyne complex where the alkyne ligand essentially acts as the bridging ligand. So this sort of a complex is formed where the alkyne ligand acts as a bridging ligand. As we have already discussed that upon complexation of the alkyne with metals, the reactivity of the alkyne ligand essentially decreases as compared to the reactivity that you see in case of free alkynes. And this allows one to do a selective reaction on the substituents of the alkynes without attacking the CC triple bond in the alkynes. And one very interesting one reaction which has a synthetic utility we will discuss over here, that is, you can take propyl alkyne, which is so this propyl alkyne cobalt complex, if you take, now you can do reaction on this alcoholic group over here. That is, if you treat it with strong acid, you can remove the OH substituent over here, and from propyl cation that is, the complex is going to be positively charged. Now, this particular compound or precursor, the intermediate complex here, can act as a new electrophilic alkylating reagent, and one can do alkylation on ketones, enol acetates, in this sort of compounds by using this as the reagent. So, you see one example here where an enol acetate essentially is alkylated by this electrophilic alkylating reagent over here. So this gives to the formation of, so this will go and this particular carbon atom will go and attack the double bond over here, and this will lead to formation of so that is, we can write both the cobalt centers at the same time over here, and this particular compound can now be, if we do oxidative decomplexation, we can isolate the free alkyne and this allows one to, this reaction therefore has a lot of synthetic utility, as we are able to alkylate, we can do electrophilic alkylation reaction by using this route. So one more reaction on the alkynes, which has a lot of synthetic utility as well as academic interest, is the cyclooligomerization of alkynes. So in presence of different metal centers, alkynes can undergo dimerization, trimerization, as well as tetramerization. And these reactions has again a lot of synthetic utility. We will see some of these reactions over here. So that is, if you take PTCl2 and do reaction with diphenyl acetylene, one will be able to isolate compounds containing cyclobutene, essentially, which forms upon dimerization of this alkyne over here. So this product is isolated. In this case, a dinuclear palladium complex is isolated, where cyclobutene is present, which forms, the cyclobutene forms because by dimerization of the acetylene ligand over here. So this sort of cyclobutene ligand formation occurs during this reaction, which again acts as a ligand to complex to form cyclobutene complex with palladium. So now for trimerization of acetylene, many of these cobalt complexes acts as very good catalyst, and one reaction that we can see, we have seen that during the discussion on metal olefins, we have spoken about this particular cobalt olefin complex that which acts as a CP-CO transfer agent, and now if you do reaction of this with an acetylene, cyclotrimerization is going to occur, and this will give rise to formation of a benzene ring, and a complex containing this newly formed benzene is going to be isolated in this way. So this reaction again has a lot of synthetic utility, and if you look at this particular compound of cobalt here, you see that it is a 20 valence electron species, as we have 9 electrons from cobalt, 5 electrons from the CP ligand, and then 6 electrons from the aryl ligand over here. So total 20 electrons are present, 20 valence electrons are present here. So one reaction which has a lot of synthetic utility is the cyclotrimerization of acetylene with nitrides, again, which proceeds in presence of cobalt complexes. That is, if you take acetylene in presence of cyclooctadiene, that is cobalt complex, you will obtain pyridine, which is a value-added chemical, and that is why this particular reaction has synthetic utility. And this reaction is known as Bornemann synthetic Bornemann reaction. Bornemann reaction, and this reaction has a lot of importance because of its synthetic utility. Another interesting reaction that, or cyclotrimerization reaction that one can do is, if you take this sort of long chain diacetylenes with terminal acetylene group over here, and then do cyclotrimerization reaction again catalyzed by cobalt complexes, that is CpCO dicarbonyl. So this will give you again cyclotrimerization. Let's make them R1 and R2. So this sort of products are obtained, and here is for 2 to 5, these products have been isolated, and again this reaction also has a lot of synthetic utility, as one can produce such substituted benzenes very easily by this particular synthetic following this particular synthetic route. So this brings us essentially to the end of this lecture. What we have learned during this lecture are the different coordination modes of alkyne ligand. We have learned that the alkyne ligand can bind to metal centers as if two orthogonal alkene units are coordinated, are present, and this allows the alkyne ligand to have several binding modes. We have seen a monodentate binding mode, two bidentate binding mode, a tridentate binding mode, as well as a tetradentate binding mode, and we have seen that two of these binding modes where the alkyne ligand acts as a 2 electron donor, while in case of the later 3 binding modes, the alkyne ligand acts as a 4 electron donor. Then we also saw the preparative methods for different metal alkyne complexes, where alkyne acts as a monodentate or bidentate ligand, and in all of these cases, when we discuss the structural parameters of these compounds as well as the spectroscopic parameters, we could see that there are 2 canonical forms of the metal alkyne complexes are possible, and depending upon the alkyne, depending upon the metal, these two, any one of these 2 canonical forms can be possible. So in one of these cases, the alkyne ligand binds to metal centers through by acceptor donor interaction, we say, and in this case, the alkyne carbon atoms retains the sp hybridization to a large extent, and also the deviation of bond angle from 180 degree, as well as the lengthening of CC bond from the typical CC bond distance that is found in case of free alkyne does not happen to a large extent. So then, in the metallocyclopropene canonical structure, we see that the carbon atoms on the alkyne carbon atoms possess more p character, and therefore the deviation of this bond angle from linear bond angle that is found in case of free alkyne is more, as well as there is a substantial lengthening of the CC bond, as we see, and that the bond distance essentially approaches the bond distance that we see in case of the alkenes. And also the CC stretching vibration can act as a benchmark to find out whether which particular canonical form of the metal alkyne complex is going to be more relevant. As the CC stretching vibration decreases substantially, we can see that the metallocyclopropene canonical form is going to be more relevant. Then we also discussed about the possibility to stabilize unstable metal alkyne ligands by complexation with different metals. So we have seen that dihalo alkynes, which are otherwise highly explosive in nature, form stable metal alkyne complexes, as well as it was possible to stabilize alkynes which have substantial ring strain by complexation with different metals, because this again is possible because of the increase in p character on the carbon atom, which allows for bent bone formation of bent bones, and this releases the ring strain in considerable amount, and therefore stable metal alkyne complexes are formed. Then we discussed about the formation of bridging metal alkyne complexes, and we have seen how a cobalt alkyne complex can be formed, where the alkyne ligand acts as a bridging ligand between two cobalt centers, and we have also seen that how the reactivity of these alkyne ligands decreases upon coordination with metal, and this allows for selective reaction on the substituents of alkynes. And this approach again has a lot of synthetic utility. We have seen that one can make an electrophilic alkylating reagent by using propagyl alkyne, and this way the propagyl cation can be formed, and this propagyl cation acts as a coordinated to this propagyl cation, which is coordinated to cobalt center, acts as a electrophilic alkylating reagent which can alkylate ketones as well as enol acetates. So then we discussed about this cyclooligomerization reaction of alkynes in presence of different metal salts, and we have seen that the palladium metal can trigger cyclodimerization reaction, and then cobalt metal can trigger cyclotrimerization reaction, and we have seen that this cyclotrimerization reaction has a lot of synthetic utility, as one can make pyridine as well as substituted benzenes by using these route. So let me conclude this lecture with this, and I thank you for being with me during this lecture.